Hey, Chemsters, this is Mrs. Vanderwally. I'm sorry I can't be with you today. I'm not there with you in body, but I certainly am with you in spirit. I hope things are going well. I hope you're having a good day. And today you're going to have Miss Vanderwally helping you with your chemistry. Uh, she's going to pass out your notes. So have those. In the meantime, find a periodic table. You can use the yellow one that I've given you some time ago, or you can find one that I've given you on the back of an objective check or something along those lines. So pause for a minute, Ms. Vanderwally. Make sure they have everything they need, and then come right back. Okay, so do you have your notes in a periodic table? I'm gonna have a periodic table up for a little bit, and I want you to kind of follow along your notes as I look at this periodic table here. And we start off with our notes with Mendeleev's periodic table. And if you recall, the narrator of last week's video was so impressed with what Mendeleev was able to do. He did a couple things. If you recall in the history, that Berzelius and Cannizzaro were both very interested in finding the average atomic masses of the elements, and they were arranging the known elements by increasing atomic mass. Then Dobereiner was the first one to recognize these triads on how, like lithium, sodium, potassium, how they have very similar properties, how fluorine, chlorine, and bromine had very similar properties. And he called those triads. Well, he was kind of um, limited because there weren't all that many elements known to make more than just a triad. So of the elements, he did a nice job at trying to organize them by their properties. And if you recall, even Newlands tried to do the same thing. So Newlands introduced the idea of the law of octaves. So he did something like this: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium. So that was his law of octaves. So that he recognized that every eighth element had a very similar property, that lithium and sodium, potassium, and then you could do the same song again, but that's okay, and go from chlorine to potassium. But then when he tried to do that with potassium, he ran into some problems. He couldn't use the law of octaves anymore. But at least it was a beginning to try to organize these elements by their properties. If you recall that Newlands was laughed at and was scoffed at and was saying that's totally ridiculous, and he kind of gave up, being very dejected. It was only a few years later, I think it was 3 years later, that Dmitry Mendeleev attempted to put both the idea of increasing atomic mass and the ideas of properties together with all known elements. And here he organized the periodic table. So he did that by understanding there are periods. Now, what's a period? Period, let me write this down here. Here we go. Oops, here we go. Are your horizontal rows, okay? And if you recall, excuse me, there are 7 periods. And even down here is your 6th period and your 7th period. So these, if you recall, kind of belong right here. So here's La and lanthanum, and then here is, oh, oops, Ac, your actinium there. And they belong in 6 and 7. And what did he do there? He organized those by increasing atomic mass. So the periods go up by atomic mass. All right, so then what? He had something called groups, and that's where he used the idea of similar properties. So groups go up and down, and if you look, there are 18 groups. We have one, two, these together would be three, four, so on, so on, so on, so on, 13, 14, 15, 16, 17, and 18. So we have 18 groups. And again, similar properties. So these are your properties. I'll put prop here, oops, properties, and these are your atomic masses. It's an M, by the way. There we go. And so Very, very, very first time groundbreaking thing that he did by combining both the atomic masses and the properties. Now, notice what happened. Take a quick look at tellurium and iodine. Look at their masses. Tellurium is like 127 point something, and iodine is like 126.9. Look at the masses. They are in the wrong order, aren't they? But what did Mendeleev did? He recognized that oxygen, sulfur, these all have very similar properties. Fluorine, chlorine, bromine, iodine all have very similar properties. So he said, well, I'm going to make an exception. I'm going to put tellurium underneath selenium. I'll put iodine underneath bromine because I believe their properties outweigh, their atomic masses. So he prioritized their properties over the masses. Now, Miss Vanderbilt, why don't you pause this and look for other cases where the atomic masses aren't exactly perfect. All right, so go ahead and pause this. All right, so did you find any more? I bet perhaps you found argon. Where's argon? Here's argon and potassium. They're not the same, are they? So argon's mass is actually higher than potassium's mass, but argon's definitely in the right spot. Did you notice anything up here in the 3D block? Did you notice that any of their masses are exactly the way they ought to be? I'm sure you could find a few others too, but in general, it is by increasing atomic mass. That's pretty cool, isn't it? So then what? Mendeleev, again in 1869, had said, well, wait a minute, there are some holes here. So there is no element known at this point at scandium, and then gallium and germanium. We don't know these elements yet. But what he did is that he predicted there will be elements there one day, and when they are, they'll have this property, they'll be this color, they'll have this density, they'll have this melting point. And by golly, when they were actually discovered, 10 years or so later, yes, they had the properties that Mendeleev had predicted. And that really gave prominence to what Mendeleev did. When those elements were discovered and Mendeleev was right, boy, that was an exciting time. Okay. What else do you notice? Remember Newland's group? He went from lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine. Then what did he do? Sodium. What didn't he hit? Neon. Why didn't he include any of this row right here? Well, it's because that row wasn't even known about when Newlands did his thing. Neither did Mendeleev. He didn't know about helium, neon, argon, krypton, xenon, and radon. Knew nothing of it. It wasn't until the Scottish scientist William Ramsay came along when he started discovering these noble gases. He saw the presence in the spectrum. He knew they ought to be around here someplace. And then he was able to isolate it from air. Really, which was not mentioned in the video, but what Ramsay needed was a way to cool air down to very, very cold temperatures. So once the idea of refrigeration came along in the late 1800s, then he was able to cool down air, and the gases would then liquefy, and he could isolate the liquid forms of these elements and find them and discover them. So he needed the refrigeration in order to add really the noble gases to the column, the periodic table. And then at the bottom, these elements were not really known at the time of Mendeleev either, especially most of these here. Think about it. These are all man-made. Mendeleev knew no man-made elements. They didn't come along until the 1930s and 1940s. I guess the 1940s was when plutonium was used, a man-made element, to make the bomb in Japan that we dropped, the second atomic bomb, which ended World War II. So Mendeleev was long dead before any of these man-made elements came about. So those were added to the periodic table after Mendeleev's group. And so then we had these unanswered questions. Why did some elements fit in order of increasing atomic mass? And why did elements exhibit this periodic behavior? Well, you might say, well, Moseley was the one that answered that first question. Why didn't they fit in a increasing atomic mass? Because of their protons. They're all perfectly arranged by order of increasing number of protons. And so why is tellurium and iodine switched? Because actually iodine has more neutrons than tellurium, and that kind of makes it so iodine is actually, I'm sorry, I said the wrong way. Tellurium has more neutrons than iodine, so tellurium's heavier than iodine, and that's why some of these others are switched. It's not because they're protons, it's because of the number of neutrons that made the atomic masses off. What else? Why did elements exhibit periodic behavior? It wasn't until our buddy Edwin Schrodinger came along where he really zeroed in on the SPD and F that really solidified this periodic behavior. We're talking about energy shells. So why do we go from sodium to potassium is because you're in a different energy shell, and that would exhibit these or explain the periodic behavior. Okay, so that leads us into the periodic law. I'll tell you what, let me just kind of switch over to your notes now. So we have this idea of periodic law, the protons and atomic number. Moseley, if you recall, let's write him down here. So Moseley was the one that came up with this idea of X-ray experiments. Oops, let me put my, here we go. So Moseley did this. And he did these X-ray experiments to reveal how to determine the number of protons. And what was then so cool is that they knew exactly how many protons every element had, that they knew where the missing elements would be, and there wouldn't be an element, let's say, between oxygen and fluorine. If oxygen has 8 protons and fluorine has 9 protons, there won't be an element in between. It has to be a whole number proton as it goes up. So that was a really big deal. And then it says the periodic table is now found to be in the atomic number order, not the atomic mass. Okay, so this is an important idea. So this explains why iodine and tellurium are in the right place, that Mendeleev was right. Sadly, Mendeleev had already died by the time Moseley discovered this, and Mendeleev never had the real proof, the real evidence, the experimental evidence of why his periodic table worked. Okay, then the periodic law, the physical and chemical properties of elements such as density and melting point, maybe you want to jot that down, are periodic functions. What does that mean? Repeating functions of their atomic numbers. So if you think of your math class, where's my, here it is, here's your math class, okay? And do you recognize what this is? It's like a sine curve, isn't it? And one cycle, oopsies, oh, Becky. So here we go. This is your sine function. And so this right here is defined as 1 period. So it's a cycle. So you go up, you come down, you come back to the same spot. That's a cycle. Up, down, that's another cycle. So that's the idea of the periodic properties. So if we were to graph something like the density, you're going to see it's a repeating motion, just like your sine curve is. Level 1, you did do the activity. Level 2, you will do the activity. You haven't done that yet. So let's go ahead and turn the page then. Okay, so I'm back to my periodic table again, and we're in section 5.2, the electron configuration of the periodic table. So again, the electron configuration in groups that can be sorted in noble gases. That's group 18. So over here is your noble gases. I'll just write Ng here, noble gases. Your representative elements, transition, intertransition, base, and electron configurations. So noble gases, what did we say in our last chapter about our noble gases? They have a filled shell. What kind of shell? Filled S and P shell. So their energy shells are filled. So I'll write this. So it has the filled S and P shells. Okay. So that neon, 2p6, argon, 3p6, krypton, 4p6. And that explains why they are so unreactive. Your representatives. So here are your representatives, and here are your representatives. All right, so the representatives, what did we say about that? Is where it has the S and P are the same period, is the same energy shell. So if this is 2s2, it's in the second period, it's in the second energy shell. 2p6, it's in the second period, it's in the second energy shell. So that's also the where your valence electrons come from, isn't it? Comes from your S and P's. Your transition elements are right here. Again, we've kind of talked about that. These are your transition. And what do we know about those? Those are filling your D shells. Okay, so this is your D shell. And what do we know about that? The period is not its energy level. So if you recall, this is your 3D. This is your 4D, but yet it's in period 4, it's in period 5. So their periods and their shells are not the same. And then these are called your inner transitions. Hang on, where are they? Down here. So your inner transitions are your F blocks. They're also called the rare earths. All right, so these are your F blocks, and we can use those as far as the periodic table. So they're the bottom ones, your F blocks. Let me go and transition to the next one because I do want to write on here. So hang on, and let me flip back to the second. Now, as you recall in our discussion from our colored periodic tables, if here is our periodic table, right? We had the staircase, right? These are our metals and these are our non-metals. Remember that? And what were the ones that are along the staircase with the exception of aluminum? Those were our metalloids. So as you go across a period, you transition from being all metals to being your metalloids to becoming non-metals, okay? They become less metallic and more non-metallic. So what I want you to do is kind of brainstorm, think to yourself, what are some properties of metals that you know of? Go ahead and pause this, Miss Vanderway. All right, did you come up with some? How about my list? You want to check out my list, see if your list has anything like yours? Metals are silvery, with the exception of, can you come up with those? Copper, and gold. All other metals are silver in color. How about this? They conduct. What do they conduct? They conduct heat and electricity. That's why your wires in your pots and pans are all made out of metals, aluminum and copper being the most common wires. What else did you come up with? What do they look like? Well, besides silvery, they're very shiny. All right. If now some of them, like your copper pennies, are your old copper pennies shiny? Is the Statue of Liberty shiny? Well, you got to be careful because what could happen is that if they're not, that means they've reacted with oxygen to form an oxide, or what's maybe called a patina. That green color of the Statue of Liberty is actually a copper patina of the copper oxide coating. It actually protects the Statue of Liberty from further corrosion. So how do you know if you have a metal or not? Well, if you have some sandpaper, scrape the top layer off, if it's shiny underneath, hey, I think you have a metal. What else can we say? Have you ever pounded a piece of metal with a hammer? If it flattens, it's malleable. Okay, you can flatten it with a hammer. And the last but not least, that most, not all, reacts with acids, forming hydrogen gas and whatever else. So that's kind of like a rule of thumb, is that most will react with acids, but if that's your only way you determine whether something's a metal or not, it's not reliable, because there are some metals like gold. Gold doesn't react with hardly anything. So it does not react with acids. You cannot say that, well, gold must not be a metal because it doesn't react, okay? What about nonmetals? Well, kind of look at our list up here, and can we compare it with the list down here? What color are nonmetals? Well, I can't really say they are one color. I'll just say they are colorful or colorless. So like carbon is black. Sulfur is yellow. Are you writing this down? Phosphorus can be red or white. Fluorine is yellow. Chlorine is yellow-green. Bromine is red. Iodine is violet. Your noble gases and oxygen and hydrogen and nitrogen, they're colorless. So there isn't one set color, but what color are they not? They're not silver. So let's write that down. They are not silver color. All right, so that's going to be a huge clue right there. Excuse me, that if you have a yellow something, I bet it's a non-metal. All right. What about the next one? Do they conduct? No, they are not conductive. Is that why, oopsies, you do not make, what is it? Oh, I see what I'm doing. Is that why you don't make wires out of carbon? That is correct. You do not make wires out of carbon. What about sulfur? Nope, don't make wires out of sulfur either. What about oxygen gas? Nope, don't make wires out of oxygen gas. Become a dumb way to make a wire. So they don't conduct heat. They don't conduct electricity. Are they shiny? No. What's the opposite of shiny? Is they're dull. All right, you don't see shiny carbon. Charcoal is not shiny. Okay, gases are not shiny, are they? The opposite of malleable is brittle. What does that mean? If I were to take a hammer to a charcoal briquette, what's going to happen to it? It's going to shatter into 1,000 little pieces of grains or something, okay? Sulfur is the same way. If you can smack a hammer to it. What about gases? You can't really call them anything. So these are the ones that are not gases or liquid in the case of bromine. All right, so you just don't classify them as anything. And finally, do they react with acids? No, not reactive with acids. All right, so what about metalloids? What did we say metalloids? Go back, look up here. What are metalloids? They're on the staircase. So they have properties of both. What the heck does that mean? That's an of. Well, they could be shiny and brittle. You see what was happening here? Shiny is a metal property. Brittle is a non-metal property. That's just one example. It could be conductive, but not reactive. Okay, so that would be another one. Conductive is like a metal. Not reacted to acids would be a non-metal. So they have properties of both. Okay, so what I'd like to do now is have Miss Vanderwaaij go over your homework with you. She has the answers. Make sure you got that, and then you're going to have an objective check, and that's the end of the day. You will have a worksheet for homework, which I'm sure you're going to get done in no time. So hopefully it was a good day. Hopefully you learned something. Hopefully you reviewed something. I'm kind of feeling a quiz coming up soon over this stuff. Now, do you remember what I told you about the quiz and the test? You may use your colored periodic table with that, so make sure you have it. Bye-bye.